Okay, so that's magic. It's not physics yet. We'll do physics later, but that's a good start on things for, well, that's not what we do in this class, and you'll see why. So I'm Lou Bloomfield. This is how things work, the spring version, 1060, Physics 1060. And my purpose or goal in this whole class, exercise, is to teach you tools for a living, to teach you how the world around you works, why it does the things it does, how to predict and anticipate things that you haven't seen before, what's possible, what's not possible, all that stuff. And so it's a physics class, but it's not a traditional physics class. Moreover, it's a class of my own creation, so we can do anything we want. And things being as they are, it's like, so if we don't follow exactly what I officially planned, who cares? The point is to convey to you something that's of value to you. So let me start off and talk about what physics is. I mean, magic is fun and games and stuff like that. And you go to science events or whatever, and there's like this bubbly thing like, ooh, that's science, wow. Well, no, it's not. It's fun and games with gadgets. What physics is about, and so physics is as a class, as an activity education, is trying to understand why things happen. So the fact that I didn't tell you anything about why the tablecloth trick works means I didn't do physics. We just did, show and tell. And my goal as we go along is to do what I consider to be sort of unmagic, the opposite of magic. Give away all the secrets. Magicians typically, hoard their secrets, try to trick you in things and disguise and baffle. On the other hand, if I don't actually explain to you or convey to you, or you don't come away understanding why something did what it did, in effect, I failed. I haven't done my job. So that's the purpose of the class, is to look at the world, physics in general, is looking at the world around us, essentially the mechanical world, as opposed perhaps to the life sciences, and explain why things happen the way they do. And it's basically an experimental field, although there are aspects of it that are strictly theoretical, but basically you look at the world around you and see how things happen and try to model them and explain them. And that's the world of physics. And what we'll try to do here, what distinguishes how things work from sort of the conventional physics classes, the conventional physics class, which as we'll see shortly, many of you already taken a conventional physics class, looks sort of principle by principle through the world and calculates up a storm and maybe eventually ties it to things that you notice in the real world, like things you actually do. I try to do the backwards approach. Look at the things of the real world and find physics in them. So I view it as case study physics. It's like, go to a business school, they're almost all, to my understanding, they're almost all case study based. You look at how, I don't know, IBM did what it did whenever. Same thing here, we look at objects or activities and try to find out how do they happen. All the gadgets that you have in life or things you routinely use, or we'll try to figure them out, okay? Another thing is, it lives in the how and why questions. So what, where, when, who questions are typically not science, but the how does it do that? Or why did this occur? That's where a lot of science shows up, physics in particular. So we'll be doing a lot of how and why question type things. And the other thing I want to say is that this is really how science was discovered. Science generally isn't just sit down and work your way principle by principle through things and the calculations. That's fine when everybody's done all the science and study everything and has sort of accumulated it like an encyclopedia. Great, you can read through the encyclopedia, but it's boring and it doesn't seem to apply to anything. So we won't do that, or try not to do that. All right. My goals. I've got various more specific ones, things like helping you develop intuition and an understanding. see our universe as predictable and non-magical, and start to realize that science isn't awful. You can actually enjoy it. And it's not something that's so formidable that you can't do it and should be intimidated by it. I hope I'm not very intimidating. The fact is, my goal is to give away everything. So if I'm up here going on about something that I'm not conveying to you and trying to make myself mightier than thou somewhere other, that's also me failing. The point is to give it all to you. And that really is the main goal of the class, is to give you stuff that you'll use and carry away with you. And 30 years from now, you'll still be using it. Before I go much further, so this is sort of I'm starting off with 2 steps to this particular class today. One is to introduce the class, perhaps introduce myself, and the other is to actually start doing what we do. And the first topic we will do, just to tell you down the road, is skating, because it's a context in which we will encounter an important physical issue that you all heard tell about, inertia. And that's what's at play really here with the tablecloth trick. So I'm going to talk a little more about the class, but I don't want to spend the whole class talking about the class. It's boring even to me. Okay? So I want to get on to skating. But before I do that, I got to sort of set the stage for the class. And one of the things, and I will try to harangue you on this a lot, is to participate. It's not part of the modern culture or experience. You will see over the course of the semester, I get on my soapboxes, and I'm not even sure whether the cultural reference to a soapbox means anything to you anymore. But back in the day, back before you could tweet, you could stand on a soapbox and pontificate. And one of my step on the soapbox pontificate things is that you all have dealt with a lot of technology, for better or worse. It's been a great thing, a terrible thing. And one of the biggest aspects, from my perspective, that I don't like is it has turned your generation into passive clickmeisters. You're itching to be back on your gadgets, many of you. And set them aside mentally. Just try to pay attention. Physics is we'll see, physics is difficult. It's difficult for me, okay? And I don't do it while I'm multitasking. And I'm not good at multitasking anyway, or I can't multitask. But y'all can't multitask. No one can do multitask and do physics meaningfully. So be here with me if you can. If you can't, well, I asked you, but whatever. Okay, so do that diversion, putting that up there was for purpose. The purpose is participate. Ask questions. Ask questions live if you can bring yourself to do it. Again, this is something that's a lost art. Please ask questions. We'll change the path of the class. It's fine. It's good. If you can't ask them live, I'll show you in a minute. There's a way of asking me electronically, and that seems to be some people's preferred path. So, get back to the mainstream here. We're going to do physics this semester. We'll do it in the context of real objects, real activities. This semester in particular is focused on a lot of electrical, electronic, magnetic, radio wave, light direction of physics. The spring is just a different path through different topics, and therefore different pieces of the world of physics. So that's the general theme of things. A few things I expect you to do. I expect you to think. And it may sound, I don't know, corny or patronizing or something, to say that thinking is hard and that many of you will be resistant to thinking, to actually just sort of essentially setting aside all the toys and the distractions and staring at a concept in your head and thinking about it long enough that it really begins to make sense. And revisiting it until it does make sense. Please do that. It's not easy. It's not, the fact that it's not easy is the problem. It's literally work to do that. And it's part of learning this stuff. Anything else in my goals? Oh, the other thing is that I've stopped using PowerPoints directly because they too are, they lend a layer of sort of passivity to the class. If I start putting stuff up there, the eyes start to glaze over and stare at the letters on the screen. And that's not wonderful. So I put what used to be my PowerPoints, and maybe what guides me sometimes in talking to you all, I put them on the web. And so let me take a second and show you sort of some resources here for you all to work with. This, wrong widget. There are way too many gadgets involved in teaching these days, and I try to use as few of them as possible. Okay. So this is my website. So it lives, and I've buried the URL. The URL for it's on one of my own servers. The URL is here. These sheets, these syllabus sheets I have are basically a snapshot of pieces of that website. So it lives on this computer, robbie.phys.virginia.edu/1060. The resources on this site that will be useful to you, I hope, are, for example, the syllabus is here if you want to see the whole syllabus, the more detailed version. But more importantly, there's a schedule of classes, and the quick link to the schedule of classes is right here. If you can see the little hand. So this is what we'll be going through. And where I started into this is my lecture notes, in effect. What I'm talking about right now live under these links. So we'll talk about skating today, falling balls down the road, ramps, and so on. So if you want PowerPoint slides to stare at, print them out yourself or look at them on your computer. I'm not going to display them anymore because we'll just get lost in them. The other thing is that I record these classes. That camera right up there is recording right now, and I'll post them online after class. And so if you miss a class, you can watch, or if you want to see a class afterwards, you want to, if I do some incredibly bad demonstration that explodes, you can watch it repeatedly. I haven't always managed to do that without spilling something. So once in a while we'll have a disaster. The best one was a flying egg that flew up in the air, broke in the air basically, broke on its way up and then rained down on one of the students in the class. It was great. So what can you do? If it doesn't explode, it wasn't fun. So the schedule of the classes is there online. It'll evolve with time because we may not cover the material exactly as I've anticipated it. It's hard to tell where we'll go, particularly if you guys ask questions. I don't have to talk about falling balls. We can drift off on something else that's interesting to people. I mean, if it's not of general interest, I won't do it. But if it's of general interest, we'll do it. The course materials, apart from coming to class, being here, and taking the exams, there being 3 of them, including the final, I would like you to read the book. Now, awkward moment, the book, which is all online, is currently not yet available through the bookstore. It's not a physical book, it's an electronic book. And here where it says, course materials, we will eventually get the book actively available under their inclusive access program. It'll be linked to Colab. So pretty much the only thing I use Colab for is for access to that book. And if you go to Colab, and the class has a site, which is this 20 such blah, blah, blah. There is a link that says UVA Digital Access, Bookstore Digital Access. That will eventually get you connected get you connected to the textbook online. And the textbook also has the homework operation. So this is necessary. You will have to get involved in that. Hopefully you'll get that fixed in the short order. Yeah, Philip?
If we had the book from last semester, would that work?
Yes, I think there are a few of you who took 1050 and already have access to this. It should continue to work. If it doesn't, nudge me and we'll see what happened. Okay? It will be a new semester. You have to register for a new semester though. Other questions? Do ask questions. The other thing is I try to get to know everybody to whatever extent I can. Names to start with. And I'm reasonably good at it, but it's hard work and I forget people's names after a while sometimes. And so I will work at it. But basically, I'm here because I like to teach students. I like to interact with students. I'm not here just to throw this stuff out there and then walk off and go do my research. So come and see me in my office hours. Come talk to me before class, within reason, after class until we're bored. Totally, it's what I do, okay? So again, this is something that is becoming something of a lost art, is just interacting, okay? So I'm happy to talk to you. My office hours, for example, this afternoon I'll be over in Alderman Cafe, my traditional Monday afternoon office hours in Alderman Cafe, 3 to 5. Come and talk. Come and say hi about it, whatever it is. Doesn't have to be physics. Yeah, please.
Is it okay if we aren't reading the sections because the textbook's not available?
Yeah, is it okay if you aren't reading the sections because the textbook's not available? And the answer is, yeah, absolutely. I mean, what can we do? Physics often takes several passes through the material to understand it anyway. So the only shortcoming of the book, having the book and having me do the class is it's the same voice twice, right? Because I wrote the book, all right, what can I do? So you hear my same jokes even my jokes about saying the same jokes. We can get all meta here. But the point is that often stuff won't make sense the first pass through. So you'll see it the first time and it's kind of like, what's going on here? The second time, maybe it's live versus on the book. Eventually it'll settle. And I have some extra videos. I have toyed with flipping the classroom, so there are even extra videos of me talking about the material, particularly for the first topics. So the more you see and discuss this stuff, and discuss it amongst yourselves. There's another thing that's somewhat lost is the interaction between you all and you all. It is often helpful to hear material and thinking of other people, particularly other people who are currently engaged in trying to understand something. Because when suddenly something clicks for one of you, you will have the ability to say things that I can't remember how to say anymore. You'll turn to your friend and go like, it makes sense to me because here's why. And it's a new voice. So do it. If you can figure out how to self-organize into study sessions somewhere other, great. Other thoughts or questions? I use iClickers sparingly. Not, I used to use them and do grading based on them and stuff. And I found I was dragging people to class who didn't want to be here and just sat around waiting to click. Or worse, they would click for 5 people. So I don't grade anything with iClickers. But if you have them, or if you can bring yourself to purchase one, I'll ask you questions and have you try to think through, puzzle through, solve the issues, the physics stuff. Along with trying to convey to you tools for living regarding physics, learning how to problem solve, to think deeply, to generalize concepts from a topic we've talked about to a topic we never talked about. These are really useful tools. And you guys are going to you're in the midst of this digital future where people who can't think and solve problems and really do something with your head that makes you somewhat unique are replaceable or automatable. It's a brave new world. So learn how to puzzle through and think, and I will try to have you do that by way of the iClickers. So let me get this out of here, and let me ask you an initial question here, which is your background. How much physics have you taken? Can you all see that okay? Should I dim the lights a little? How many want me to dim the lights? Raise your hand. Okay, a little bit. All right, I can dim the lights a little so you can read it better. If I dim it too much, the snoring starts. So let me ask this question. For those of you who do have an iClicker, if you don't, who cares? I always use AA as the channel if that means anything to you. So let me just ask this and go ahead and click in. How much physics have you taken in the past? From my perspective, the results are almost always identical, year to year, class to class. Okay, we'll go to 30 seconds and then we'll call it. So something on the order of 45 of you have eye clickers already, which is great. All right, let's call it a day here. Click, and I can show you the results. C. So, yeah, okay, we've got a few people from, one person from Princeton. Okay, but most of you have taken about a year of physics, give or take, okay? The median person has done that. So for those of you who haven't taken any physics, so in the A category, or even in the E, it will turn out not to make all that much difference. So don't worry if you're in the A category here, or don't be too confident if you're in E here. It works out okay. The next question I'll ask you, and then that'll be done for my introduction sort of part of the world, is 6 physical quantities. I'll ask you, can you distinguish between velocity and acceleration? And I realize that these are just words, which is not exactly physics, but they're words that are pretty central to physics, and so you might well know them. Velocity from acceleration, mass from weight, and force from momentum. How comfortable are you with those? You okay with the idea? Questions about the question? See what you think. Now we'll go to 20 or so seconds in. You all pretty much decided here. Okay, 3, 2, 1. Okay, so we're getting almost a majority at probably can distinguish them. So that said, that the first week or 2 or 3 of the class will have a fair amount of review for you, or solidifying those ideas, because we will go right after those. We'll go after them in context, I intend, but by the time this is done, I would hope that all of you can go in the E category. Yeah, you definitely can distinguish velocity from acceleration and so on. Okay, anything else? Let me blank that guy off here for the moment. The last of the sort of starting up stuff. Anything else I want to? Oh, what's expected of you? I mean, apart from just lofty goals and so on. Most importantly, there will be 10 homework assignments, what I call problem sets, which will be online at this Wiley publisher's website once we all get connected to it. And the point of the homeworks is they're not quizzes. There are things to think about. They're questions. You can come and go and take them, but think about the questions until you're sure you got the right answer. They're not just like, let's guess and get the job done, okay? They're meant as learning experiences, not as assessment tools, okay? And this is based on lots of experience in physics education, that if you're not actively engaged in struggling with the problems, you don't learn the stuff. You can listen to me go talk about it and you go, yeah, it makes sense, and then it just evaporates until you suffer over it. I mean, I know this from experience as a student myself. It was the late nights. As a physics grad student, they're late nights. You're sitting there doing these calculations. It's the act of doing those where you really learn the stuff. So the same thing with the homeworks. They're to get you to learn the stuff, not to just blow it off, just to blast through it at the last minute. So get them done in a timely fashion. They're all due on Wednesdays. And you're welcome to talk about them among yourselves. There's nothing pledged about them. Talk about them among yourselves. Don't farm them out, but rather the point is to learn the material. So ideally you would all get them right because you all understand them by the time you click make your choices. They're all multiple choice. And I have office hours on Monday afternoons and Wednesday mornings. So come talk to me about the problems if you're having problems with them, okay? Ideally you get them all right. The other graded component of the class, and that's all there is, right? The exams and the homeworks, right, are 2 midterms and a final. And another thing on the website, just to show you, another resource that you should be aware of under resources here, and let me put it up so you can see it, and I can't just tell silly jokes about things you can't see. Okay, all the old exams for like forever are up here. This is the right. So you want to see last spring's final exam? There it is. And I encourage you, and I will further encourage you, take the old exams before you take the real one. Take an old one. And I've got the answers up there too. You can go look at the answers. So it's in the act of struggling with these questions that you learn the stuff. So I'm not doing you a favor giving away the old tests, or it doesn't matter. The issue is struggling over the old questions is great. It's a great it's a great learning experience. So there they are. Last details. This room is open, available, and I'll often be here the hour before 1. So we've kept this thing free for years. It's always under pressure to be used for other classes. But so I often come in, I don't necessarily come here like at 12, but I'm often here 20, 30, 40 minutes ahead of class. Come and talk to me if you like. Certainly you can come in and get settled. And after class, no hurry to get out of here either. So come talk to me after class. Do the demonstrations. You want to do the tablecloth trick? Go for it. Some of these demonstrations, I mean, it's just fun to do them. Some of them you actually learn from the act of doing it because you can't see the complexity involved in some of the. You can't feel by viewing. You can't feel some of the demonstrations have physical aspects to them that you can't appreciate until you do it yourself. All right? And some of the things we're doing with electrical things that are fun. You have no other opportunity to do this, so do it. Anything else? The rear doors, I'll point out that they exist. You can come in this way and go out this way, but you also can go out the back, and sometimes we get traffic jams here, so the back is fine. Those of you who have time pressure to come from another class or to go to another class, it's fine. I mean, it's just part of life. If you have to go out early or arrive late, it doesn't matter. I'm usually oblivious to this stuff. As I say, I can't multitask. Doing physics and teaching physics, I can't do anything else. So I won't be able to tell you who came and went. It just happens, like, blows right by me. All right. Any other questions, things on your mind about the class? I've not done a perfect job of introducing all the details. We do have this lingering issue over the book. Once the book does appear, if nothing else, I will contact you all and tell you, ooh, it's there, okay? I will do my best to get that done as quickly as possible. Okay, that said, let me stop talking about the class and start doing it. And the first topic, so this is the first case study, is skating. How does skating work? And the part of skating that I really want to focus on is probably the boringest part, really, the starting and stopping and coasting, and we're not going to worry about playing hockey and all that stuff. We're just going to worry about the very simple issues of, like, when I used to have rollers. I used to have inline skates, but so I'll make do with a Razor scooter. I could go get yeah. I guess Lime came and went. I don't know what the current scooters are around grounds. I mostly encounter the scooters by throwing them into the weeds when people park them really inappropriately. Okay, so here's the idea with skating. And the issues that I really want to start digging into are, if a skater is just standing still on the ice, it could be ice, it could be wheels, I don't care, and it doesn't make a lot of difference. When they're just sitting still on the ice, they have this remarkable tendency to stay still on the ice. You have never seen a skater just standing there. I'm picturing a little kid just standing there, and suddenly they head off at 20 miles an hour, right? Just for no reason. It never happens. I mean, yeah. So the observation is that a skater who is standing still tends to stay standing still. And the other, and to get moving, something has to act on them. They don't do it for free. They do it because something pushes them. So, object at rest, okay? The other thing is that when a skater is moving, they tend to keep moving, and particularly they tend to keep moving the same way they were. They don't reverse direction all of a sudden or suddenly go to the side. They tend to just continue doing what they were doing. And so that's the context in which you'll start looking at how the world works. The fact that I pick skating is, it's okay. It could be all kinds of sort of coasting activities, things on wheels, bicycles, wagons, and skateboards. Let's tease apart the physics that's in those questions. Why does the skater at rest stay at rest? Why does the skater that's moving keep moving in a particular way? What's going on there? And okay, so the first demonstration, which I've already done, but now I'm going to do it put the physics in, is this one, right? The tablecloth trick. And I'll risk doing it twice. This, incidentally, is pink disappearing ink for obvious reasons. And yes, I have worn it before and enjoyed watching it disappear. All right, so the idea is this, that I'm going to set up a slippery tablecloth. Why slippery? Because there's this phenomena that we're not going to be paying much attention to yet, known as friction. And you know friction, right? Friction is an influence, at the very least, it's an influence that mucks up the simplicity that I'm trying to give you, talk about in the context of skating. The reason, do this right. In these early days, I will set aside nuisances in the real world that just make life complicated for us in trying to talk about physics. So right now, I'm setting aside friction. It's there, I can't get rid of it completely. But the story I want to tell you regarding skating is simple if I can just leave the nuisances out. So here's what's going on. I'm setting up objects. They're not skaters anymore. They happen to be table setting pieces. And like the skater, when you leave them alone, they tend to keep doing what they were doing, whatever it was they were doing. So a skater at rest tends to stay at rest. A skater in motion tends to continue in motion in a particular way it will come to. That's an observation about the world. It involves potentially, you could call it laws of motion. They're not laws like we're used to in society where someone made decisions and imposed them. These are laws of nature that we inherit. They come to us and we have no choice over them. They are the way the world works. And one of the laws about the way the world works is that if you leave objects alone, and I'll have to pin down what that means, they keep doing what they were doing in the way of moving. So an object at rest, whether it's a skater or whether it's the place settings, tends to stay at rest if you leave it alone. Is that okay enough? I mean, it's lots of vague language in there that I got to pin down. But basically, if you leave it alone, it'll stay doing what it's doing, and I'm going to almost leave it alone. I can't quite leave it alone because there will be some friction going on here, but I can minimize the effect of friction, and I do that by going fast with a slippery tablecloth. But here's the idea then. These objects will stay put, not because something's holding them there, but because that is their nature. Objects at rest tend to stay at rest. You know this phenomena under the name inertia. So this is the first half of inertia. So you want a name for this observation or general character of nature is things that are at rest tend to stay at rest. The name for that would be inertia. All right? So these are going to stay there because of inertia. It's their nature. And my job is to not bother them so that they do what nature intends. That is to stay put. Is everybody okay with that idea? Ready? Get set. At least I got reasonable, didn't get wet, okay? I get complacent after a while and I do a less excellent job. Okay, so that's why the stuff stay there, inertia. Well, we can keep going with inertia, but before I do, let me ask you one more question here. Get this out of the way. So this is, again, going towards a real-world application. So yeah, I'm drifting between different topics. So skating, I'll set skating aside for a second and go after something seemingly completely different. Rotary lawnmower. Where did that come from? Okay, it just did. A rotary lawnmower is most lawnmowers these days. They are devices that sit on the grass. They have an engine usually, although sometimes that's an electric motor, that spins a blade very rapidly around in a circle. So there's a cutting blade going around and around inside this lawnmower. And it cuts the grass. So the question is, the grass is normally rooted in the ground. So the grasses are sticking up, the green guys, and they have roots going down into the dirt. What if they didn't have roots? Could you still cut the grass? You okay with the question, or any questions about the question? It's a yes/no question. Can a rotary lawnmower cut grass if the grasses aren't rooted? They're just sitting there on the surface of the ground, still sticking up, but not rooted. You're okay with the question? I'm taking you at your word. All right, so try it. And I will allow you, go ahead and talk among yourselves about this. You want to discuss it with your neighbor. Say hi to your neighbor. Know somebody in the class. All right, I'll give you to the minute and then we'll call it. 5, 4, 3, 2, 1, 0. Oh, come on, there it is. Okay, so there's a majority going for no. Yeah, and D, we often get one of those. All right, so remember this. I'm not going to answer this quite yet. The majority are going for no, you can't do it. But let me give you a couple more demonstrations. Again, physics is all, in my view, I'm an experimental physicist, so I'm biased here, but it's all about the experiments. Whatever ideas you come up with, they better agree with experiment. So let's play with inertia a little bit here. And here's the idea. I'm going to take an apple, this apple, and it's not connected to anything. I'm just going to set it here on the table. And for a certain number of years, I would do this experiment with this knife. I have to talk through the story anyway. I would do this up here with this knife, and I would say, here we go, right? Okay. For obvious reasons, I stopped doing that. Okay. So I'm going to set that mild-mannered little, all by itself apple. It's just going to sit there minding its own business. And I have this spring-loaded knife now. And watch what I'm going to do. I'm going to take the spring-loaded knife back, and I'm going to let go of the spring-loaded knife. And it's the apple's fault. I didn't do anything. The apple was just sitting there, and the blade snuck through it. Not perfectly. There's a little bit of friction around again. But basically, the apple was sitting there. And what do you think made this apple sit there? You tell me. Why did the apple stay there? Inertia. That's its nature. It's an object at rest, staying at rest. And we didn't bother it much. I mean, okay, cut it in half. But the reason the apple stayed put was not because something held it there, but rather because that is its nature. If you don't push it much, and we'll talk about pushing shortly, it just does what it was doing. Sits there, motionless. Was motionless, remains motionless. And the knife snuck through it. Everybody okay with that idea? I've got a question for you guys to answer. Look familiar? Rotary lawnmower. Blade comes by very fast. Grass sitting up there, no roots. Can the blade cut it? Go for it. Someone will still pick D. We'll go to 5, 4, 3, 2, 1, 0. Thank you. Yeah. It's fun. All right. So the answer is absolutely. You don't need the grass to be rooted in the ground. I get into quibbles with people online sometimes over whether there's an airflow due to the blade spinning and stuff, and that there is airflow, and it does make life a little more complicated and stuff. But again, we're setting aside all the nuisance effects. The main issue in a rotary lawnmower is the blade goes so fast, and this is important, that they deliberately go fast, to just go through the grass before the grass has time to really change its speed. It's motionless and stays motionless, it gets cut. Yeah, please. Is this ignoring the weight of the machine and wouldn't it knock over the grass? The machine does its best to sit above the grass without smooshing it. So you probably have seen that if you use a rotary lawnmower, where the wheels go doesn't cut properly often, because now the machine is messing up its own ability to cut. But the grasses that are sitting up there minding their own business, they just get sliced by a fast-moving blade. Other questions? And this is true, this is for more relevant topics maybe than in a lawnmower, because you all aren't thinking about cutting grass. But for food processors and blenders, how do they manage to slice up all the food or the ice for the beverages on this weekend? What's holding the ice there? Nothing. The blade just sneaks through the ice, and it goes fast. Again, or coffee grinders, same idea. They have to go fast because if you go slow, you're not leaving you're not following the rules. You're not leaving the apple or grass to itself. It's like me pulling the tablecloth slowly. Now the nuisance effects become important. And they mask the simplicity of inertia. Okay, so you're okay with an object at rest tends to stay at rest because that's its nature, not because something's holding it there, as long as you don't bug it. Yeah? In a world without friction, would speed matter? In fact, no. It depends on the context, but the tablecloth trick would work perfectly with it. If there were no friction, I could go as slow as I liked. If this knife were so sharp that it exerted no force on the apple, I could take my leisure to go through it. Thanks for asking questions. It's good. It's important. Other questions? Okay, so that's the first half, sort of inertia. And we'll see down the road that inertia has deep underpinnings in the world of in the context of what's known as momentum. But this is the first half of inertia. We'll build the whole inertia, and then 2 weeks from now, 3 weeks from now, I'll go back and go this is why inertia was what it was, because we'll be talking about momentum. The other half of inertia then is what? It's an object that's in motion tends to continue in motion. So the skater, once the skater's going, you leave the skater alone, they keep going. And more particularly, they tend to go in a straight line at a steady pace. So they don't veer to the side, and they cover equal distances in equal times, which is the fancy way of saying steady pace. We'll pin down language later, probably not today. So that's, again, an observation about the real world. This is how skaters move. It's how objects in the absence of friction move. This is a little gadget that gets rid of friction because it's an air puck. It's floating on its own wind. So if I get it going, it tends to keep going. So that is the nature of things. And of course, I have fruit examples of this. So this is the object at rest, staying at rest. Well, if I let go of the banana and I could get rid of gravity, I can't get rid of gravity. Gravity is another nuisance for today. If I could get rid of gravity, so we're just floating around, and I let go, it would just hover, right? Because it's an object at rest, staying at rest, and then I could sneak the blade through it. I can make gravity unimportant by going fast, okay? Flesh wound, okay. Better, okay? So again, the banana just was sort of complicated by the presence of gravity, but basically the banana was sitting there only because of inertia and the blade went through it. But the other half of inertia is this one. If I get the banana moving, it was, and okay, I have to start with, get the knife out of there. If I get the banana moving, while I'm pushing on it, this is not an inertia story, it's too complicated. Well, it's for another day. But once I let go of it, apart from gravity, it's an object just by itself. And it will move because of inertia. Inertial load. Now, I can't get rid of gravity, and gravity messes my story up. So if I could get rid of gravity, I could get it moving, and it would just coast along. And the word coasting is the right word. It's a reference to an object that's moving as inertia had in mind. That's what coasting means. So if I could get rid of gravity, it would coast all the way to the wall. I can't get rid of gravity, but I can work fast again. So, okay, straight line, steady pace. All right. Got lots of bananas. All right. So this time, and I'm obviously not going to chase the banana with my right hand. Ready? It was the banana's fault. I had nothing to do with it. The banana coasted through the knife blade because of inertia. Nothing pushed it. I didn't push it. See? Hand's still there. So the continuing motion, straight line, steady pace, is just the way of nature. Gravity is around. I had to set it aside by going fast. But the banana just coasted through the knife, and the knife divided the banana. Okay, so those are the two halves of inertia. That whole idea is codified in what's known as Newton's first law. So it's probably a pretty good place to close with. Newton's first law makes an observation about the world and really sort of tries to pin down this notion of inertia. And what it says in simple language, not finally the best language yet, is that an object that's free of external influences moves in a straight line at a steady pace. And oddly enough, that is a comprehensive statement. It includes the motionless, because physicists are perfectly comfortable with the idea of moving at no movement. So an object that is not moving at all is still moving in a straight line at a steady pace. It's just not much, right? Zero. So that is what things do. You leave them alone. That is no external influence, which we have to pin down. Moves at a straight line, in a straight line at a steady pace, which we'll get better language for on Wednesday.